In this question, we've been asked to determine the empirical formula of a mystery hydrocarbon. And within the question, we've been supplied various pieces of information about the hydrocarbon, such as the masses of carbon dioxide produced, as well as the mass of water produced. And we've also been told that the hydrocarbon was burned in excess oxygen. Now, how would I approach this? Well, first of all, the hydrocarbon was burned in excess oxygen. This is significant for working out our answer. The implication of the fact that the hydrocarbon was burned in excess oxygen means that for whatever hydrogen was in the hydrocarbon initially, right, the total hydrogen produced, which occurs in the H₂O, there's effectively a 1-to-1 ratio between that. So the hydrogen which was in the hydrocarbon has a 1-to-1 ratio with the hydrogen in the H₂O, effectively, or in aggregate. This is specifically in terms of the moles specifically of hydrogen. And for carbon, right, the carbon, similarly, the moles of carbon in the hydrocarbon is effectively, when it turns into carbon in the form of the carbon dioxide, specifically the moles of carbon is in a 1-to-1 ratio, right? And this is effectively what the excess oxygen part tells us, because the implication of excess oxygen is that complete combustion took place, okay? Complete combustion. And so that effectively means that we can assume that there wasn't necessarily other byproducts, right? So there wasn't, for example, carbon monoxide, for example, because obviously if there was a significant, like for example, if there was carbon monoxide as a byproduct, obviously this contains carbon, right? So we would obviously be in some level of difficulty to say, well, there was a 1-to-1 ratio between the carbon in the hydrocarbon and the carbon in the carbon dioxide. But because it's complete combustion, we can actually say, yeah, that's effectively what we can assume happened. Now, from here, we've also been given these masses. What do we do with them? Well, we need to figure out what are the moles of the carbon dioxide and what's the moles of the water, because this is the first step towards figuring out, well, what was the moles of the carbon, what were the moles of the hydrogen in the original hydrocarbon, okay? So in order to do that, we remember the equation relating moles, mass, and molar mass, being that moles n is equal let's just use general approach first. So the moles is equal to the mass, m, divided by the molar mass, right, which is mr. Therefore, in this particular case, we need to, let's first work out what the molar masses are of CO₂ and of H₂O, right? Now, you may know these already, so, you know, if you do, you can feel free to kind of write those down, but we can get this, or we can work this out from the periodic table effectively. And so I've just got a few extracts from the periodic table: carbon, hydrogen, oxygen. So for CO₂, we're going to need to multiply the occurrence of carbon by the relative atomic mass, plus the same for the oxygen. So for carbon, it's 12 times 1 plus the oxygen. So this is going to be 16 times 2. And if you do that, what you should get is 44, right? And if we do the same for H₂O, so in this case it's 1, right? So it's 1 times 2 plus what it is for oxygen, which is going to be 16 times 1, right? So if you work that out, you should get 18, okay? So we know that the MR of the CO2 is 44, and we know that the MR for H₂O is 18, okay? So given those numbers which we have, what we're going to do now is work out the moles of the CO2 and the moles of the H₂O, right? And we're going to do that using this relationship. So the moles of CO2, let's start with that. That's therefore going to be the mass, which is 91.696 divided by the molar mass, which in this case is 44, right? And for H₂O, got the moles then of H₂O, it's going to be equal to 46.89, right? Divided by 18, right? Okay, now given this, anyway, so at this stage I would advise, okay, have a go at working out what these are in your calculator. Okay, and if you had a go, you should find that for the CO2 we get 2.084, and for the H₂O we should find is you get 2.605, right? Okay, so now at this stage, what we're gonna do is we can represent this as a ratio. So moles of CO2 as a ratio of the moles of H₂O, right? So that's effectively 2.084 and in this case 2.605. Now at this stage, what we need to also remember is the fact that the H₂O is not, we're looking for moles of hydrogen, right? In terms of carbon, we know there's a 1-to-1 ratio, so we can say, okay, the moles of carbon, actually just carbon, not CO2, moles of carbon is the same, it's 1-to-1 ratio. The moles, I'm just going to write this down, so the moles of carbon in terms of that and the moles of CO2, we know that that is a 1-to-1 ratio, right? It's 1-to-1. So that is, yeah, so the moles of carbon is therefore 2.084. But when we look at H₂O and we look at the moles of hydrogen, it's not quite the same. So the moles of hydrogen, when we compare it to the moles of H₂O, it's not a 1-to-1 ratio, because for every mole of H₂O, we've got 2 moles of hydrogen, right? So you can see H2 therefore got 2 moles. So this is effectively a 2-to-1 ratio. Now what's the implications of this for this ratio? Is that if we want to convert this into a moles of hydrogen, right? Right, so if we want to convert this into a moles of hydrogen, we must multiply it by 2. So this value, 2.605, we do need to multiply that by 2, right? And so I would invite you to have a go at working out what that is. And if you do multiply it by 2, you should get 5.21, okay? 5.21. And at this stage, remember what we're trying to do is we're trying to get the simplest whole number ratio, okay? Obviously in the current situation, as we see what we've got here, we do not have a whole number ratio, right? But we need the whole number ratio, or at least that's what we're trying to work out. So at this stage, what we're going to do is we're going to divide both sides by 2.084. Okay, so 2.084. Divide this side as well, 2.084. Right, and what does that give us? Well, this part is straightforward. If we divide 2.084 by itself, we get 1, right? With regards to this side, I would invite you to work out what that is on your calculator, right? But if you do have a go at that, what you should get is 2.5. Okay. So do we have the simplest whole number ratio yet? Well, no, we don't, because this is not a whole number. At this stage, the next step is to look at progressively multiplying both sides by a number which will give both sides a whole number ratio, right? And so the first number we could try is just multiplying both sides by 2, okay? So what I'm going to do is just multiply this by 2, multiply it by 2. What do we get? So if we do that, we're going to get 2 here, and we're going to get 5 here. Now the question again arises, is this now our simplest whole number ratio? And at this stage, yes, we now have the simplest whole number ratio, but as you saw, we did have to scale it up by multiplying it by 2 in order to get there, right? And so at this stage, what we can say is that for carbon, in the empirical formula, for carbon the coefficient would be a 2, and in comparison to when we compare it to the hydrogen, the coefficient for the hydrogen is going to be a 5, right? Now what we're going to do actually, we're going to need to put this into a proper formula, right? So this is kind of just a hand-wavy way of just showing, okay, this is the number associated, but the actual formula is what is going to be C2H5, right? And so do we now have our empirical formula? Is this the simplest whole number ratio? And the answer in this case is yes. This is our simplest whole number ratio. So in this particular, for this particular question, the empirical formula is C2H5.